So at Berkeley, your focus was to reduce the computational burden of the stacking. I promised we would get back to stacking of the stacking methods developed by your advisor, Mark Vanderlaan, to scale machine learning to very large data sets. So, could you explain this topic of stacking methods and then maybe more specifically your research on how um, you were able to adapt stacking methods for very large data sets?
Yeah, sure. So yeah, that's kind of one of the things that I focused on in my PhD. And it really just kind of came about from just using the software that was available to do stacking. And it was just taking like a really, really long time to run my models. And like, there's like one point where I calculated it was going to take like 2 weeks to run like this model that I wanted to run with like multi-level cross-validation and stuff like that. And so, yeah, I was just a little bit like, I think one of my first classes at Berkeley was with my advisor, and he, introduced what he calls it the superlearner algorithm, because he has a paper called Superlearner, which basically proves all the theory behind stacking and why it works. So stacking existed a lot like earlier than people knew how exactly it worked and were able to publish like theoretical guarantees of performance and things like that. So that's why he calls it superlearner. So he's, presenting this algorithm, and he says, this algorithm provably does better than any single algorithm. And I, raised my hand and I'm like, okay, well, if that's true, like, why have I, first of all, never heard of it? And second of all, why isn't everybody using it all the time? Like, if you had one algorithm that was always better, why wouldn't you just use that one? It doesn't make any sense to me. And he's just like, I don't know. I don't know why they don't use it. So I was like, this doesn't make any sense. So, I kind of like early on, actually before I went to Berkeley, I knew about Superlearner, and I just didn't understand why people weren't using it. But then I started to try to use it, in my research. I also did some applied research, and it was just, it was slow. It was, training a whole bunch of algorithms in R, right. And all the code was in R. And so it was just, it wasn't scalable to big data sets. And I worked in like biostatistics. So a lot of the data sets are smaller anyway. So people aren't testing it on like, million rows or anything like that. So, right. So yeah, basically I just was like, this needs to have a better user experience. Because I like the algorithm, but it's like not working for me right now, the software. So one of the things I did was discover H2O around that time, which had an R library. Oh. And so that was through like some other projects and benchmarking and another startup that I used to work at. So I discovered H2O, and I realized through like extensive benchmarking that this platform is really fast, really low memory, like has a bunch of algorithms, not as many back then as we do now. But I was like, maybe instead of using a bunch of random R packages that are implemented by all different people with different skill sets, and some of them are really slow, you don't even know which ones are slow in advance. So basically I saw that as a platform that I could develop the superlearner / stacking algorithm on top of, because it didn't have it. So I started just writing that code and making that software. I first started out as an R package that was using the H2O R package. So all the code I wrote was in R. But really it's just kind of instructional code. It's not just saying train this algorithm and then, take these cross-validation folds and do this with them. And it didn't really matter in terms of performance. It was written in R, but it was as an R package. And then eventually I graduated and then went to go work at H2O, and then we re-implemented everything in Java. So yeah, H2O is written in Java, but it has all the algorithms are written in Java, but the APIs are Python and R is how people mostly use it. So yeah, we got it all, super optimized in Java with some Java engineers that I worked with. And and so then that was one approach. Then there was a couple other things There's another algorithm that was called subsymbol, which is kind of a version of stacking, but it's partitions the data set into subsets and then uses this kind of fancy version of cross-validation where it's able to you're able to score all the rows like you need to in stacking, but you're able to do that with like training on smaller subsets. And it actually does pretty well compared to if you just use the whole data set. So that was another approach. And there's an R package that does that. It would be great to have it in H2O. We were just talking about it the other day. It's been a minute, but like maybe we could get that into H2O. It would be cool. Yeah.
So that was all super interesting, but I still don't feel like I know exactly what stacking is.
Oh, okay. So let me tell you. Okay, stacking. So it's really simple. So you just cross-validate a set of algorithms. Let's say you have 5 algorithms, or like, not 5 algorithms, but 5 models, like a random forest with these particular parameters and a GBM with these, and et cetera, et cetera. And then you train and cross-validate those k times if you're doing k-fold cross-validation. And then what you do is then from that process, you have the holdout predictions from each fold. And so you have like a prediction for each row in the data. And then you so basically you kind of imagine like a new matrix that's your training matrix, and there's still n rows as the original training frame. But now there's just, if you had 5 algorithms, there'd be 5 columns. And each column is just the cross-validated predictions from each of the algorithms. And so you have this new thing, you can stick on the response column, and then you have this new training matrix, and then you train another algorithm to learn how to best combine the predictions from the base learners to predict the outcome. So there's 2 machine learning problems going on. The original one on the original data set, and then this meta-learning process. So, and you can use any kind of algorithm you want for the meta-learner. Often people just use a GLM, but you could use whatever you want. So it's basically just a 2-level system where, you have the base learners, you have the meta learner. And then when you go to use that in production or wherever to score new data sets, you have to score all the base learners, get the outputs, put it into the meta learner, and then get the final prediction. So one of the things that can be slow about stacking is if you have, let's say, hundreds of base learners, and especially if any of them are particularly slow at generating predictions, you're kind of, hopefully you could do that in parallel. Maybe it wouldn't be a big deal, but you're limited in that way. So sometimes people, think it's too complex or something like that, but it's, I don't think it's any more complex than deep learning, and people love that.
Yeah, no, that is actually quite intuitive. And so I wasn't aware, but so at my machine learning company, Nebula, our main production algorithm is a stacked algorithm. I just didn't know that it was called that.
Oh, nice.
So we do exactly that. We have multiple base learners that feed into a generalized linear model that allow us to have this meta learning output. So we kind of intuitively stumbled upon that. We're like, we get, in some situations, one of these models performs really well. In other situations, this other model performs really well. Let's try to find a way to have the best of both worlds.
Yeah, I feel that it's been discovered independently many times, I think, which is, again, probably why my advisor discovered it and then like proved all the theory behind it. And I'm not, I don't know if he actually knew about it before that, actually. So it's become a popular technique on Kaggle. That's pretty much where you see it a lot. But yeah, people are using it. Like a lot of our customers use it.
It makes a lot of sense.
Yeah,
it's like, to me intuitively, as I kind of just explained, like some kinds of models, like a GBM or XGBoost, they happen to excel in particular kinds of situations. By averaging together models that excel in different kinds of situations, Yeah, it's unsurprising to hear that they're doing really well in Kaggle competitions too. Anyway, I spoke over you.
That's okay. I'm glad you're stacking. You should try H2 AutoML though. That's my pitch.